which is now.
Thank you, Patrick. And thank you for having me here. It's a pleasure. Also, when I'm in the right time zone, it's even more a pleasure. I will be talking today about graph drawings and graph limits. And my talk is based on joint work with Marthe Bonamy and my supervisor, Bojan Mohar. The first part, I will talk a little bit about graph drawings, especially graph drawings on the sphere, and motivate a little bit why graph drawings in the sphere are so beautiful. And then I switch more to graph theory and talk about graph limits, a theory introduced by Lovász. And then at the end, on the last slides, I will combine these two and show how we can do this. So first motivation to study graph drawings on the sphere is because a lot of graph drawings naturally are on the sphere, on the globe. Like, for example, here, communication networks or flight networks. So that is one motivation, but there's also a very good mathematical reason. I'll come to that in a minute. Just as a reminder, so graph drawings on a surface are similar to graph drawings on the plane. So vertices correspond to points on the surface and edges to simple curves. And usually we don't want the curves to self-intersect. Also, as in the plane, we can find crossings. And actually, I will be talking a little bit about crossings. So let me just pull up a picture of a nice graph. Here is K5, and K5 is not planar. So however we're going to draw it in the plane or actually on the sphere, it doesn't matter, because the plane and the sphere, they have the same genus. And there's actually, a stereographic projection from the sphere to the plane. So drawing on the sphere or the plane are equivalent. But however we're going to draw K5, there's always going to be at least one crossing. And here's a drawing where it has exactly one crossing. So we say the crossing number is 1. So in more generality, the crossing number is the minimum number of crossings we can achieve when drawing the graph on the sphere. And the 0 here will be for the genus 0. Yeah. So there's a huge conjecture since the 1960s about the complete graph. So a very easy graph in general, but it turns out when we draw the complete graph, we don't even know its crossing number. So it is conjectured that the crossing number of the complete graph is this number here, which is roughly 1/64 n to the power of 4. And why this is conjectured is because there are drawings which achieve this bound, and but it's hard to find lower bounds in general. And one drawing which does achieve this bound could be, for example, on the sphere, and actually this is the drawing that Guy found in 1960. We can split the vertices of the complete graph into 2 parts. Half of the vertices we put at the top around the North Pole, say, and the other half we put at the bottom, say the South Pole, on a same circles. And when we do that, and then we put in some edges, and I only drew a few of them to one vertex, but actually if we start drawing more, so say all the edges will be present at the end, I'm not gonna put them in, it's gonna be a bit confusing. And we do that, so we take these shortest lines between the points, then we actually exactly gonna achieve this number. So these are what we currently know the best ways of drawing the complete graph. There's no drawings with fewer crossings. And in 2007, the best current known bound was found by Baloch, Ledecky, and Salazar. And here I just put in the asymptotic constant, and it is quite close to the 1/64 from the conjecture, but there's still some error term. So not only do we not know if this number is correct, but we also don't know if these asymptotic are correct yet. But there is actually this constant 1/64 appears quite a lot, and there's reason to believe that this might be right. But it would, I think, be quite difficult to prove that is exactly 1/64. I would like to discuss some other type of drawings which give us few crossings, which are basically random drawings on the sphere. So what we do in the first step, we take our favorite probability measure, and simplest would be the uniform distribution on the sphere, and we pick endpoints at random. Then we end up with a number of points, and what we do in the second step, we connect them by geodesics, which are the shortest paths. And from that we get, if we connect any 2 points, we get a drawing of the complete graph. So first to note that this only depends on the location of the vertices. So once we pick them, we exactly know which drawing we are talking about. And Moon showed in 1965 that if mu is the uniform distribution, then if we pick these endpoints randomly from the sphere, this gives us a drawing which has this expected number, roughly 1/64 n to the power of 4. Yeah, so what does this mean? That basically, when we take random drawings, that this are very good drawings. They have very few crossings. And in fact, this number that I put in here, this is the expected number of crossings. And when we compare this to the bound we had before, the best known bound, here, then they are quite close. So here we will have something like n times n-1 times n-2 times n-3/64. And here we kind of see the same numbers, n-1, n-2, n-3, and just that we have them rounded down. So yeah, in expectation, we have very few crossings. And why this is so beautiful is because here we have like these geodesic drawings. And if we wanted to do the same, say on the plane, we would pick a few points and connect them by straight lines. That wouldn't work as well. And the reason is mainly that when we have straight line drawings or geometric drawings in the plane, then we can never actually, however we draw them, we can never achieve this 1/64 bound. It's always going to be bigger. What we did, we extended this result to more general probability distributions. So it's a very long word. We called it non-degenerate antipodal symmetric probability distribution. But it includes basically everything, all the words that we need to understand it. And I'll just explain them. So we have the word non-degenerate, and that usually we say non-degenerate in the plane if no 3 points are collinear. And here it's similar. We say no 3 points are on one great circle. So basically no 3 points have the same geodesic circle. And that's just a property from graph drawings that we like, because let's say we draw a line here from this point to this point, it would overlap with the other 2 lines that we draw. And that's not valid in a drawing. And the second property that we want is antipodally symmetric. So what does this mean for us? When we have one set, like this set, let's call it A, and we have some measure on the set by our probability distribution, we want that the antipodal set here has the same measure. So, for example, the uniform distribution, it has these two properties, just because the measure just depends on the area, for example, and the probability that 3 points are on the same circle is 0, because it's a smaller dimensional space of this 3-dimensional ball. But we can imagine way more general drawings. So, for example, if we had a sphere and we would not take the uniform distribution on the whole sphere, but let's say we just set the distribution to have a value at the top and at the bottom, but they need to be antipodally symmetric, not like I drew it, then we could do it. Or, but I mean, then what would happen is that we would get a lot of vertices at the top and a lot of vertices at the middle, and no vertices at the bottom and no vertices at the middle. And that actually, such a drawing also has few crossings. So it's quite nice. And we can even think of just putting them maybe on a line even, and then we will recover the drawing that I showed you in the beginning. So this is our theorem. And yeah, I said everything about it already. So let us go a little bit to another type of graph, the complete bipartite graph. Similarly easy, so we just have 2 parts and an M and all the edges between them. And actually before, this was actually conjectured before the complete graph in 1955 by Zarankiewicz and Urbank, that the crossing number of the complete bipartite graph is this number over here, which is roughly n squared m squared over 16. So this problem is also called the Tehran brick factory problem, because basically when Tehran had to work in the Second World War, there were kilns and there were storage sites, and every time, and between those, there were kind of, for the wagons, the, how do you say, ways to push the wagons through. But every time they would intersect these, I'm missing the English word, Schienen. Do you know?
Rail, maybe?
Yeah, right, rails. And it would be harder to push these wagons. So the question was, how can we rearrange these sites and kilns to make it easier? And this corresponds to a complete bipartite graph, because from every kiln to every storage site, they had these rails. Yes, so here also, similar to the complete graph, lower bounds are difficult to find, and random geodesic points on the sphere give a good bound. And here again, we can find drawings which exactly attain this bound, but these are not the drawings that were first found. So first, actually, for the complete bipartite graph, you can draw it in the plane with straight line edges and attain a good bound, actually attain the Zarankiewicz bound. So here, using straight lines actually works. But we can also do a construction on the sphere, and I'm going to explain why it's useful and what type of drawing attains this bound. So again, we gave it a very nice name, Antipodal geodesic drawing. And in these drawings, so we have these 2 bipartite classes. One is blue here, it has size 4, and one is red here, it has size 4 as well. And in each bipartite class, we want to have antipodal points. So say here we have B1 in the red class, then we also want its antipodal point, which I called here B1 bar. We also want it to be in the bipartite class. Yeah, and here we would have V2 and V2 bar. And so this will be only for n even. And the second property is just that these edges are geodesics. So whenever we have such a drawing, it actually attains the Zarankiewicz bound. And the nice thing about these drawings is that they are very variable. So for example, here we could move this vertex W2 wherever we like, as long as we also move its antipodal point and still get a drawing with the same crossing number. And so for K44, as it's drawn here, it doesn't really make a difference. But we found that in general, for bigger complete bipartite graphs, we actually get a lot of different drawings. So using the sphere, it gives us to describe a whole range of drawings which achieves the Zarankiewicz bound. Whereas in the plane, there's just one very standard one. And the next thing we asked is, so all these drawings have the same number of crossings, but we wondered, can we describe them more, or can we say how the crossings are structured in general? And to think about the structure of crossings, what we looked at is the intersection graph. So in the intersection graph, basically for each edge, here, for example, W2, B2, we have a vertex. And vertices are connected, here, for example, W1, B2 and W2, B1, if when we look at the edges, they cross in the drawing. So in this case, it looks very easy, the intersection graph, but this is only because we just looking at K44. So when we look at very big drawings of the complete graph and the intersection graph, this intersection graph can have any subgraph that you like, triangles, for example, 4 cycles and so on. So then we decided to look a little bit more closer into it. So one thing that we already said, so the number of edges in the crossing graph is the number of crossings in the drawing. And this gives us some kind of edge density when we divide by a normalizing factor. And this normalizing factor is the number of vertices choose 2, which is just as if it was a complete graph. So the maximum number of edges possible. And the vertices of the intersection graph is just the edges of the complete bipartite graph. And as we said at the beginning, the drawings that we are going to look at, these antipodal geodesic drawings, all have the same number of crossings. It was roughly 116 n to the 4. And if we divide it by this number, and because we have this 2 here, this gives us roughly 1/8. Okay, so this is, we know this value. The next, say, interesting value that's a little bit more difficult, but also still easy, is to look at triangles. So it's basically, we look at our intersection graph and ask how many triangles are there and divide again by a normalizing factor. And basically a triangle in the intersection graph is the same as 3 edges in the drawing, which pairwise cross each other. And to make our life a little bit easier, we looked at very special antipodal geodesic drawings, which are like blow-up drawings. So we always started with the K44, the one that you already saw in the beginning. And each vertex we replaced basically by n vertices on a small circle. So instead of 1, we would have a bunch. And this is still going to be, we're kind of blowing up that vertex. So, and this is still going to be a complete bipartite graph. The sizes will be 4n and 4n of the bipartite classes. And what is happening here is, here we have one edge, and this one edge is going to be blown up to n squared edges. And why we do that is because, well, we can still kind of describe where our vertices are placed. So then we can still calculate where our crossings. So this really helps us when we try and count something. What we did, we looked how triangles, sum of triangles converges to when we let n go to infinity. And what is true then is that the triangle densities converge to values within this interval, which is roughly 0.0068 and 0.01. So these are our triangle densities, and they are always going to be in this interval, but we can also attain anything that is in this interval. And how we can do this, so let's say we wanted a lot of crossing triangles, and we would start with the drawing of our K44, like here, where these angles, alpha, beta, gamma, and delta, are very small. And if we wanted a drawing with few crossing triangles, then we would start with a drawing where these angles are roughly pi half. And then we have one drawing and another drawing, and we can attain anything in between when we continuously move from one drawing to the other. Yeah, so this is what we found. And how did we find that? Well, it's basically just counting. So you look at your drawing and you characterize your crossing triangles depending on where the edges are located. So you have these what we called edge bundles. And for example, here you have the red and the blue edge, which cross within one edge bundle. And you have the yellow edge, which crosses in the other edge bundle. So this could be one type. And you, for example, you can count how many red-blue edges there are. It just depends on the location of these end vertices here. And there's going to be another 2 vertices down somewhere here. And then any yellow edge going from here through this bundle is going to cross the other 2. And then this, you get a number of how many you have. Then you could look at another type. For example, here all 3 vertices are incident to this blown up vertex. And when you do that properly, you actually get quite a long formula. And this formula only depends on these angles, alpha, beta, gamma, and delta, that you have in the K44 you start with. And basically, arrow to big O of R, which depends on the radius of the small circles that you choose to place your vertices on. Okay, so these are triangle densities. Maybe this is already some kind of limit that we're looking at, and properties of maybe a limiting object that we're looking at. So let me explain now a little bit the theory by Lovász about graph limits. So that's quite a young topic, 15 years old. And it also talks about densities. So here is this parameter THG, and this is kind of a probability that a random map from a small graph H to a big graph G preserves edges. So here's our small graph H. It's just a path of length 2. And we asked, what is the probability that mapping it into G will preserve its edges? So here we have 2 examples. And while this first one is very natural, the second one, the vertex 2 and 3, they are mapped to the same vertex here, but we say that still is edge preserving. So it is a little bit different than counting just the subgraphs H in the graph. But usually how it turns out is that these cases down here that are kind of not H subgraphs, they are of a smaller order term. So really that is really just counting usually densities.
Sorry, so just to make sure, by preserving edges, you mean that the neighbors or the incident vertices of an edge either get mapped to incident vertices or to the same in that case?
Yeah, so what I mean by that is here we have a one-to edge, and here is the one-to edge is preserved because we mapped 2 and 3 to this.
Sorry, I missed the labels. Yeah, okay. So 2 edges can get mapped to the same.
Exactly, that's a good way to put it.
Yeah, okay. But my question would have been, so what if 1 and 2 got mapped to the same vertex? Would that still be edge preserving, or I mean, maybe it doesn't matter?
That would not be edge preserving.
Okay, thanks.
But you're right, it wouldn't matter because it's usually a smaller order term. And what Lovász showed, or first he defined, sequence of graphs, and they are growing graphs, so the number of vertices increases. Usually one doesn't have to define it like that. But we say that the sequence of graph is convergent if all these densities for every graph H converges. So in our case that we looked at crossing graphs, x1, x2, and so on, and we saw that the triangle densities, so for H being a triangle, converged. But to show that the series converges, we would have to show that each of these densities converges. Then Lovász showed that there exists actually a limiting object W, and he called this limiting object a graphon. And it is some type of infinite graph, but it's not countably infinite. And the next slides, I will try to explain and give an intuition what this limiting object is. And this is really going to be mostly talking about graphs and graph theory now. So let me start with an example of the complete graph and its adjacency matrix. So basically the vertices or the columns and rows are labeled as the labels of the vertices, and we see a 1 if the vertices are connected. So here we say zeros because the vertex would not be connected to itself. And if we look at the bigger adjacency matrix, what kind of happens is we see more 1s and less zeros. And if we take a bigger and bigger, you can imagine taking a bigger and bigger complete graph, but leaving the square the same size, most of the space will be occupied by 1s, and then only some of the space will be occupied by zeros. So actually, how we can imagine the graphon or how it's defined, in this case, or say always, it's a map from a square, 0, 1 by 0, 1 square, to 0, 1 values, or value between 0 and 1 actually. And for the complete graph, the limit would be just the all 1s map from the square. So this was quite an easy example, but more complicated graphs have more complicated graphons, and it's more difficult to actually describe them. And why are these graphons interesting, or why are they useful? So if we do have a graphon, we can actually usually also sample a graph out of it. So how could this look like? So here, this is my 0, 1, 0, 1 square. Let's say here is 0, 1, 0, 1. And I put as numbers the values of my graphon. So my graphon is 1 on this square, 0 on these squares, and so on. So how we could think of how sampling from a graphon works? Well, intuitively, we would just put 1s where we see a 1 and 0 where we see zeros. So this is not exactly how it works, but this is how we can imagine it to be. In general, we would, we would do something slightly different. We would solve an integral, but if we do solve it, it is actually going to look really like similar. So it is going to give us some kind of probability distribution. And in this case, because we have ones and zeros, it is actually exactly going to look like this. So we can go from the graphon actually to a sequence of graphs which are going to converge to this graphon. So once we have the graphon, we can ask, how does a representative look like? Okay. I don't have to really say that, but here A would be somehow a complete graph. So we would have all edges, and then we would have some part B and C in general, and B will be a complete graph because we have a 1 here. So there's all the edges within B, and then we have edges between B and C. So if this is B, we have some edges between, all the edges between B and C. So this would be just how an example graph would look like. And obviously we can have values which are not 0 or 1, and then it becomes a little bit different. So here, this is a graphon, and again, I put in here a value, it's 1/2, and zeros here. And we can again think of here having set A, here having a set B. This is set A again of vertices, and this is set B. So the graphon we look at is actually the graphon for random bipartite graphs. The 1/2 just tells us that with probability 1/2, we put an edge between A and B. And what is true, if you just take a random sequence of bipartite graphs, they are going to converge to this graphon. So it's kind of, obviously they will not look like that. They will have some ones and zeros, but they are going to converge to this.
Hi, sorry, I'm a bit new to this graphon thing. So basically in the previous example, I mean, so the probability signifies, I mean, if it was 1/d, then it will be 1/d, right? In these places. That's the idea, right? And so if it was a complete bipartite graph, it will be 0, 1, 1, 0, the graphon.
Yeah.
Okay, I see. Okay.
Yeah, so yeah. So if we have 1/d, then we have 1/d times the number of edges.
Okay, right.
Okay, so we can stop. No, it's a good question. It's the first time is always a little bit confusing. So these graphons give us actually a bridge between sequences of graphs, which are combinatorial, to an analytic object, which is a function from the square to 0, 1, and it has to be symmetric because generally, adjacency matrices are symmetric, and it is measurable and it has to be measurable. So from a graphon, we can get the sequence, and from a sequence, we can get the graphon, but only if the sequence converges.
Sorry, is this an if and only if? So if I give you a function from the square to the interval, which is symmetric and measurable, is it a graphon?
Yeah. So
okay.
In our example, we didn't need measurable because our examples were measurable, but in general, every graphon is measurable. Like when you have a sequence and it converges, then the resulting graphon is measurable. And when you have something measurable, then you have a graphon.
Cool, thanks.
And here I should probably put sequences of graphs which converge, because just random, random sequences converge too, but yeah, not every sequence converges. And our connection is between sequences of drawings, and using the intersection graphs, we get a sequence of graphs, and then we can say that we have a graphon. So that's basically the outline of this last part that I will talk about. And as an example, random drawings, because I find them quite nice because they give us few number of crossings. but actually sequences of graphs that could be the blow-up drawings we talked about in the beginning, and so on. So let us suppose we take these random drawings, but this time for the complete bipartite graph. So we have two non-degenerate probability measures on, say, the sphere. And we pick endpoints with respect to the first probability measure, and then endpoints with respect to the second probability measure. Example, yeah, we said, so in the beginning, we could take measures on some kind of circles here. And this means that we draw our red vertices from these circles, and then more or less, we're going to get these blow up drawings for very large, because we're going to have roughly the same number. If it's uniform, we'll have roughly the same number of vertices on each circle. And then they're going to be also roughly the same space apart. And then this will give us random blow up drawings. Or we could just think about uniformly taking the red and the blue points. And then we get a picture maybe like this. And what we do again, we have these randomly sampled points and we connect them. Here we have two classes. So we're going to look at the complete bipartite graph between the red and the blue points. Then what we could show at these type of geodesic drawings and its intersection or crossing graph, if we look at these and look at the sequence of this intersection graph, then it is going to be converging to a graphon, actually with probability 1. But what usually is true, that we know that this graphon exists, but it's actually quite difficult to describe. So it would be really nice if there was a way to describe this one. And how can we prove such result? So by the theory of Lovász, what we need to show that these densities converges to all graphs H. And the main idea is to show that the expectation converges to some value pH, and then show that the variance is small, and then use Borel-Cantelli lemma. And then we know that actually not only the expectation converges, but the value itself. So it's a very standard proof to do. But why I put it in here is because it's actually quite interesting, or probably easy to see, what these expectations converge to. And the reason is, so here's the crossing graph, right? Let's say we want to know the density of the triangles. So H would be here, the triangle. So in the drawing, this will look like these crossing triangles, these three edges that pairwise cross. So if we want to know the expected number of them, all we need to know is what is the expectation that 3 random segments on the sphere cross. This is some value pH. So we know that these expectations have to converge against this pH, because it's just sum of expectation, right? We think about what is the probability that these edges give us this crossing triangle, and summing over all of them, and then dividing through all choices. It's actually exactly going to be pH. And what is nice, this is actually connected to what is called Sylvester's 4-point probability. So if we ask for H to just be an edge in the crossing graph, which is a crossing in the drawing, then this pH would then be the Sylvester's 4-point probability on the sphere. So that is the concept in probabilistic geometry. So this is in some way, calculating this pH is also a generalization of these geometric probabilities. So I think it would be really nice if one could calculate those. But that's quite difficult. So this theorem that I put down here, I said, okay, we take these geodesic drawings of the complete bipartite graph, and we take probability measures on the sphere and so on. But actually, it doesn't really matter to be on the sphere. We could be on any surface which is geometric, where we can define these geodesics, and we only need to make sure that what we get at the end will be a drawing. And also that most of the time there's only one geodesic to choose from, because if there's multiple geodesics to choose from, this is not gonna be well defined. But basically we could do it on a torus, on a double torus, triple torus, and so on. So no matter on which surface we draw, randomly with respect to some probability measures that are non-degenerate, then the sequence of intersection graph is always going to converge. Yeah, so it would be nice to look at some of these surfaces, maybe some sequences. Maybe in some cases we can describe this graph on W very well. Open question that arises directly from this line of research is, can we describe the graphon for blow-up drawings? So for blow-up drawings, we already knew these triangle probabilities, and they were quite, still it was quite a difficult formula, but maybe if one chooses the particular nice drawing to start with and blow it up, maybe there's an easy way to describe the graphon for this. And what is maybe even a little bit more interesting is if we start with the sphere and take our points randomly from the sphere with respect to the uniform distribution, can we describe the graphon there? And one thing that we could already not really compute, well, first of all, we made a guess. And so here we thought at the beginning that the graphon might look like this. So here red are edges, I mean, how to read this. So here at the top will be edges, because edges of the drawing, because vertices in the crossing graph are edges of the drawing. Or maybe I should say d infinity. And then 1 means that they likely cross, and which is here depicted in red, and 0 means that the edges likely do not cross. And why we thought the graphon might look like this is because we ordered the edges by its length. So if we have 2 edges with short lengths, then they cross probably not. And if we have edges which are very long, then they might or very often cross. Maybe this is rather 1/2 down here than 1, but still when they are longer, they are crossed more often. So we were thinking this could be the graphon, but we tried to do some integration with what we thought this could be, and it turned out that it didn't really work out. So somehow one has to think of another way of how this graphon could be represented. And we could also not show one thing that we should be able to, like when you have the graphon, you should be able to get any density from it. And similarly, if you have all densities, you should be able to describe your graphon. But we looked at these triangle densities for the uniform distribution on the sphere. And this was already quite difficult to calculate. So we've seen at the beginning that having densities of just edge crossings is really easy to calculate for the uniform distribution. It was this 1/64 n to the 4 number. But for the triangles, this seems much, much harder. So I think this would be really nice to find out. And computationally, we ran some simulation and just looked at 3 segments and the probability that they form a crossing triangle, and was something like 0.0075. And this is in between kind of the two values that I showed earlier today for the blow up drawings. That was something like 0.0068 and 0.01. Yeah, so I didn't give much hope that this might be quite difficult, but these are like, let's calculate what this is, which seems hard. But we could also just ask more topological questions. How do graphons for intersection graphs looks like? If we have a sequence of graphs which converges and random drawings of these graphs on the sphere, does then the sequence of the drawing converge? Things like that. So a lot of questions to ask here. Yeah, I think we have one last slide. Yeah, thank you.
All right, thank you very much for your talk. Are there any questions? Yeah, Arno?
Hi, thank you for the great talk. I had a question about the generalization for surfaces. Like during the whole talk, you were talking about the round sphere. And when you talk about other surfaces, are you putting some specific metric on them, like constant curvature, or is there no assumption?
I mean, how we only thought so far about hyperbolic geometries with constant curvature -1, I think, is it right? For hyperbolic. Yeah. So, but I do believe, I don't know if you cannot really equip any other geometry. I mean, you can make the curvature change it, but I think it wouldn't really matter how exactly the curvature is, as long as you can define the geometry on it. But I do think that curvature -1 is just work, and the others.
Okay, and my second question was about these geodesic drawings. Like in general, when you're on a surface, there's an infinity of geodesics between any 2 points, because you can twist around the surface as much as you want. So are you looking for geodesics that minimize the distance, like globally and not only locally, to define your drawings?
Yeah, so you take the one of shortest length.
Okay, okay. Thank you.
All right, are there any other questions? So I have one actually. So for the original problem where you were taking random points on the sphere, another way of kind of taking some kind of random points would be to take random order types instead. And I know that for certain problems, somehow random points from a uniform measure and random order types behave very different. So has this been studied? Like the crossing number if you take a random order type instead?
So you mean we look at the local rotation or something like this?
For example, I guess, yeah, that's one way.
Well, oh, sorry. What do you mean by order types? I think I'm a little bit confused.
Yeah, so I mean, order types I mainly know in the plane, but you can also do them on a sphere. So an order type is just the orientation of the triple. So for each triple, you get its orientation, and then you get a whole, so the equivalence class of point sets, which have the same orientation system, that's called an order type. And you can also sample uniformly from the set of all order types. And that's somehow kind of different than just sampling uniform points. So I was just wondering if you know of any work that has looked at it.
No, I haven't.
Okay, interesting.
Yeah.
All right.
Oh, and I also have for Arno maybe just a little explanation to what we might want. So we can do in the double torus. We can embed it in the hyperbolic plane like this when we cut it open. And yeah, so it's actually quite easy to find the smallest. So let's say you have 2 points in here. and this is the hyperbolic plane, maybe not exactly like this. So H, then, I mean, you could have the smallest here, but you can also look at the copy of this one somewhere else in your plane. So here you would have another copy of your double torus. So maybe if this is U and this is V and this is your other copy of V, you can look if say this is smaller, but you only need to look at finitely many of these copies V in the hyperbolic space, and then say here maybe 20, and then you can actually decide which one is the shortest path. So
Okay.
Yeah, computationally that's also possible to do. And then once you found the smallest one, you can ask, okay, let's say this was the smallest, and then you have your second path. You can ask if they cross or not.
Okay, yeah.
Yeah.
Thank you.
All right, do we have any other questions?
So I have a question, but I'm not sure it makes much sense. So thinking in terms of drawings in the plane for points in general position, not only is there a smallest crossing number, but for straight line drawings, you can get a range of crossing numbers. So for example, for K4, there's a drawing with 1 crossing, or there's a drawing with 0 crossings. And so the question is, if you look at a general complete graph and you look at this family of drawings that have minimum number of crossings and maximum number of crossing, is there any interest in studying what happens for those kinds of families of drawings?
Yeah, so on the sphere, we only looked at the ones with the minimum number of crossings. That's not like the best bound. We haven't really looked at other drawings. When we think about these triangle densities and want to say, okay, we take the one with the smallest number of crossings and the smallest number of triangles, that could be interesting, but there maybe we can compute this graphon at the end, because maybe that's the most nicest one of them, because it's actually going to look so this could be a good idea to try, I think. So what's going to happen is that might be the one with the most the smallest number of triangles. It's actually one that where they are kind of positioned before. Anyways, they're kind of positioned quite naturally, but I think, now that I think about it, maybe it would be still quite difficult, because they actually have to converge against the border, and this is how you get the smallest one. And when they converge against the border, but it will have to be a little bit different. So yeah, okay, maybe I cannot give a good explanation right now, but this minimum is only attained in, like, not really attained, but it's an open interval. So there is a sequence of drawings that converges, but there is not one minimum. So that might be difficult to do. So yeah, I don't know. Sorry, I said at the end something different than I said at the beginning, but now I remember that this might actually be quite difficult. Yeah. But yeah, we haven't looked at other classes, so one could think about yeah, I don't even know what is the maximum number of crossings on the sphere with geodesic drawings, things like that. I'm not quite sure.
All right.
Can I ask the last question, sir?
Sure.
Thanks. Suppose I give you two measures on the sphere, and let's say they're very nice, absolutely continuous with respect to the Haar measure. And then, well, I don't give them to you. I just tell you, here are the graphons that I got out of using these two measures with the process you're defining. And let's say the two graphons are the same. Can you say something about the original measures? Can you say they're actually the same measure, some rotation?
Yeah, this would also be a good question to ask. We don't know. So all these.
What's your guess?
Yeah, I mean, I guess they would be. I mean, you would have at least topologically equivalent drawings. So you would expect to see at least the same topology on your drawings. If this implies that you have the same measure, I'm not sure.
Okay.
Yeah.
Thanks.
All right. Do we have a final question? That doesn't seem to be the case. So thanks again, Alexandra. And thank you, everybody, for joining.